because I want to move on pretty quickly to the advection diffusion equation. So based on this result, I'm going to go over here and think about the advection diffusion equation, where I'm going to include the advective code that I just showed you and the diffusion code from last time. So let's see how this is going to work. And I changed the T's to C's here to represent concentration because I'm more fully on a tephra problem. And this is what the expression looks like. So this is exactly that term, the change in concentration as a function of time, going to be equal to the change in concentration as a function of x times the wind velocity. I should have made that a v, sorry, it's w in this case. The change in the wind velocity in the other direction, change in concentration in y. I'm going to come back to this term in a second. And then over here, these are these diffusion terms that I used last time. So this is the gradient and the concentration in the x direction, gradient and the concentration in the y direction. And k is the diffusion coefficient. And here I'm just saying that the diffusion is the same in the x direction as in the y direction. It could be different, but usually it's not. Well, it definitely is not in the atmosphere. The atmosphere is isotropic in its properties. Maybe if you're dealing with a groundwater problem or gas flow inside the earth, you might make these diffusion constants different, representing some anisotropy and permeability or something like that. And then this capital sigma over here, that's the source term. So that's the tephra getting dumped into the model, the volcano erupting into the space. And then finally, I have another advective term here, which looks a little bit different. That's V in the z direction, the change in concentration in the z direction. And essentially that's accounting for the fact that the particles are going to settle in the atmosphere, right? They're going to settle out in the atmosphere, and they'll be settling by using some settling velocity. And in most tephra models, almost everybody uses an expression for the settling velocity that Costanza Bonadonna and Steve Sparks and somebody else, oh no, Gerald Ernst came up with. And so basically they look at a Stokes settling model and they implemented that in codes like tephra 2, and then codes like Fall 3D or Ash 3D or whatever use that same Stokes settling velocity model that Costanza came up with as part of her dissertation. So that's the settling velocity. So I'll come back to that in a minute and describe that a little bit more when we get on to tephra. But right now, what I want to do is two things. One is I want to remind you that if it happens, you're a little intimidated by this equation. I know the first few years I used it, maybe a few decades I used it. I was a little bit intimidated by the equation, but I relax when I look at the units of these expressions. So here I'm just using essentially a dimensional analysis. I'm saying that I've got a mass, that's the concentration per unit volume, say, in the numerator, and length cubed times t in the denominator. Well, that's this expression, right? So I've got the mass in kilograms divided by a unit volume, meters cubed, that's the concentration, also divided by t, which is time. So that's how I write that. And then if I go to the next term, you can see I've got a velocity times the concentration as a function of x. And you can prove to yourself that represents this, that is the length over time is the velocity, and the mass divided by the length scale to the fourth is the cubic meters times the dx, right? And so obviously those L's cancel, and I've got mass over L cubed T here. And all these terms all of them have to have those same dimensions because we're just doing addition here, right? So the units of this have to equal the units of this, have to equal the units of this. So if you think about it sort of in the opposite way, well, where did these differential equations come from? You know, ultimately, people are starting to think about those equations from the point of view of a dimensional analysis. So you can always more or less understand the equations by unpacking them using dimensions, right? So that's why I spend the time doing that. Okay. But now I want to forget about the settling velocity. let's just implement a simple solution to the advection diffusion equation for a second. And so here it is. That's exactly the same expression. And we're going to implement this one in code. And the only difference is forgetting about this term. So you can say, okay, well, the settling velocity is 0. Particles are not settling out of the model as I implement this code. It just turns out to be a little bit easier to implement right out of the box. So I'm going to do that. So we've already solved this, right? I've already solved this part. Sort of these terms are all solved by the 2D advection equation, right? It looks like just like what we went through before, except it was equal to 0, right? Because that was all that was happening was things were advecting. And now on the right-hand side, I've now added this diffusion term, right? I'm saying, okay, well, I've got diffusion as well. And I've got a diffusion coefficient, just like I did last week. And that's the amount of diffusion that happens as a function of time is going to depend on the diffusion coefficient and the gradient in the concentration. And this is the source term. This is like how much material I'm adding to the atmosphere, say, in each time step, right? So each time step, the volcano is erupting and I'm adding material. You know, that could be constant. You can make that a variable, you know, whatever you want to do, right? Whatever floats your boat in terms of that. So what I'm saying is all the pieces are there, and I didn't write out all those finite difference expressions again. They're the same ones, okay? So I'm gonna go down here. I think I better run this one while I'm thinking about it. Oh geez, come on. I'll try that again. I'm gonna run that. And then here's my my functions. Now I've got two functions. I've got the Lax-Wendroff 2D advection equation, which we just implemented. This is written slightly differently, but basically it's the same. To implement that solution in 2D. And I solve for the future based on the time now minus the advection in the x direction minus the advection in the y direction, okay? And I make a copy and I return it. And then I have the diffusion equation, and I just copied and pasted this diffusion equation out of the notebook from last week. So that's it. So now I've got two functions which I'm going to deal with. Notice I didn't rewrite any code. That's kind of nice. Well, actually I did for this guy, but I didn't have to. So I just made it a little bit neater. But in principle, you don't have to rewrite any code to implement this. Okay. So let's the source is psi, not sigma. Jeez. Chuck. Or what is that? Phi, it's capital Phi. Jeez. I think I'd know my Greek alphabet. There we go. Okay. So so we're going to develop a test run, and we're going to have a source that's placed at the center of the grid, just like the problem we did before. And we're going to have a simple model that steps through the expression. It steps through those equations. So here, I'm just going to implement my my equations here Again, I'm going to have my model domain. That's W equals H equals 5,000 meters on a side, say. dx dt is going to be 10 meters. So for the diffusion equation, I need dx squared and dy squared. So I just do that to make things simpler. I have the velocity field. I need that for the advection part of the equation. So if this is wind velocity, it's -5 and -5. Then I have my material. I'm just using the same sort of temperature model as I used before, but it could be particle concentration or whatever. It's 200 and 1200. I implement the time step. This just worked for this problem. I need to go back and look at this time step in a little bit more detail and figure out what's going on. But I saw this time step was numerically stable, and I implemented with the diffusion coefficient. I do the same thing I did before, making the initial conditions and stuff like that, right? So I run that, and okay, now I'm going to iterate through this. I'll just go ahead and do it. Should take a minute, and while it's going on, let's look at this expression. So I'm going through 1,500 time steps. And I'm just going through the time steps, m in the range of the time steps, and I'm calling the Lax-Wendroff 2D advection equation, just like I did before, but instead of just looping from there, I then call the 2D diffusion equation, right? So I go through one step in time in advection, and then one step in time of diffusion. Then I reset my source term, which was phi, capital Phi, and I said that's the volcano plume or the temperature source or whatever you want is persisting, right? It's always there in the simulation. And so then you run it, and this is what you get. Okay, so this is, whoops, what happened? Sorry. I lost the plot, literally. Okay, so this is the solution to the advection diffusion equation. And so what you can see is material is advecting. In this case, it's being blown by the wind field to the northwest. And that's causing this elongation in the plume. It looks pretty much like our model output did down here. You know, it's going out there, but you notice here there's very little diffusion, at least perpendicular to the axis of the velocity vector. And so it's going out, and as I get further from the source, the plume is getting wider and wider, and that's the diffusion term, right? So that's being governed by the diffusion. So if I, you know, I can go up here and I can change these constants. Like, let's say I make the diffusion, I don't know what'll happen. Let's make the diffusion twice as much in that direction. And so I run that, and then I've got to iterate through it again. It'll take a minute. And we'll just see what the output is of changing that diffusion. So while that's cranking along, whoops, okay, I got a little numerically unstable there. And so I got an error message. Woe was me. So let me run that. Yeah, okay, didn't work, okay, because I was out, my time step no longer worked, was no longer appropriate. I told you I had to work on that, but okay, let's go the opposite way. Let's try 50. And let's run that again. I don't want those pink boxes because that basically is a clue. It's becoming numerically unstable as I go along. So I would have to change that delta T equation, which I didn't implement very well in this particular case. So I didn't get any pink there, and so that's good. I implement that. It doesn't look too different, does it? I decreased the diffusion. Must be a bit narrower than it was before. Okay, so that's the 2D advection diffusion equation, and that seems to work okay. The reason it looks better than the 2D advection equation is now at every step, when I get my advection model, and there might be a little numerical instability in there, I then kind of smooth it out with the diffusion equation. So if I really have an advection diffusion problem where diffusion is occurring with advection, I can smooth out the model and get away with a little bit more by coupling the two equations in this way, step by step. First calling the advection term and then calling the diffusion term. So there's no real advantage in this case in solving it all in one step. So this is a perfectly legit way to do it, as long as my steps are small, but scaled by grid spacing and the diffusion term, which we just discovered, and other factors. Okay, so that's that. Okay, now if you were going to stop there with this model, you really wouldn't have to have a numerical implementation of the advection diffusion equation. In fact, you can probably come up with a pretty good analytical solution for this problem with these simple conditions. But usually what people do is they want something to be a little bit more realistic. So I'll go to the bottom here. Here I implemented it a little bit differently. I said, let's say there's a source of gas or something down here at the bottom of my model, and that gas is rising at some velocity through the model domain, and it's moving, it's being blown in the negative direction in the x dimension, the horizontal dimension, but that velocity is varying as a function of depth or height or whatever you want to call it. So this plume is bending over. And so, when you go to AGU and people show, these cool looking models with complicated patterns or gas flux through the earth or, tephra dispersion in the atmosphere, what they're doing is they're changing the implementation of the advection diffusion equation in a pretty simple way. So let's take a look at that. So now what I've done, I think I'll start here. What I've done is I said, okay, I think everything else is the same here in this, except let's look at the wind field for a second. Okay, so I said, well, in the simple model, the wind field is constant in the y direction, the vertical direction. It's -5. That is, particles are rising upward at some velocity. You could make that expression more complicated, but let's just stick with that. Then I'm saying, well, I'm going to change the wind speed as a function of height in the sorry, didn't say that right. I'll change the horizontal wind velocity as a function of height in the model. So in other words, as I go down here, you can see that in the output, the horizontal velocity close to the source is pretty small. So the plume is rising pretty much vertically. As I get higher and higher, I'm increasing the velocity in the x direction. So the plume is bending over more and more, right? So it's kind of just a very simple tweak to this model to make it more interesting. And so here I implement that change in code. Two things have happened. One is, notice I now make the velocity in the y direction and the velocity in the x direction arrays. Okay, so I'm going to allow my velocity to change as a function of horizontal and vertical distance, or whatever my model domain represents. So here now, remember before Vy was just equal to 5. That was it. Now it's equal to an -5 in an array of nx by ny, right? So I'm specifying it's -5 everywhere in the model domain. And I just start out by specifying the horizontal velocity is 0 everywhere in the model domain. And I did that because I'm about to change it. So here's a pretty simple way to change that. You can implement it in other ways as well. But I'm just stepping through all my x-axis, all my values, and I'm saying, okay, I'm gonna let wx change. That is, the horizontal velocity is changing as I step through the model, right? So I'm basically putting a gradient in the horizontal velocity. Put in my initial conditions. In this expression, I move the source out of the middle and to the bottom. And I do the same thing I did before, where I step through Lax-Wendroff 2D advection with all its works, and I step through the 2D diffusion equation, and I add source incrementally, or I add concentration incrementally at each time, and then I just graph that result. So that's the what it looks like after, say, 1,000 seconds in this particular model with this scale. So what I'm hoping you take away from this is that the advection diffusion equation is there. I sort of lost my scale here. There we go. The advection diffusion equation is sort of complicated looking, but first of all, I can break it up into parts, totally legit. So I can deal with the advection and the diffusion, make my life easier. I can do the finite approximation to this equation as long as my time step is small enough not to cause numerical instability. And I can add a source anytime, source term anytime to this equation. So, if you're dealing with a gas flux problem, maybe that's the SO2 coming out of the volcano. Or if you're dealing with a tephra problem, it's the flux of tephra out of the volcano, putting it into a specific level in the atmosphere. So then you just implement it, and you can start getting pretty images. And what makes that useful from a modeling perspective is you can begin to change boundary conditions and change parameters and things like this, and things like that. So it's nice. And so I suggested a couple applications for you down here. You can think of the plume rise maybe as a buoyancy problem, right? And there are a couple different ways to approach that. One is you can use something called the Briggs equations to talk about how buoyant a plume is, either in the atmosphere or in the ground or whatever. Briggs actually cared about pollution, industrial pollution. He was developing these equations to understand sort of the concentration of particles downwind of smokestacks, stuff like that. But he also implemented it in a gas diffusion problem. They got really concerned about methane in the ground and where methane was going from pollution sources and stuff like that. So anyway, he simplified this problem by saying there's something called a buoyancy parameter, and then a horizontal wind speed, and then an atmospheric stability factor. So I did this for the tephra problem, obviously. And so the height it's going to rise to is going to be equal to this expression. And so you could simply alter your wind velocities to reflect that simplified expression of the buoyancy of the plume and generate a bent over plume, right? That's a simple way to do it. You can also consider buoyancy-driven flow directly, where if you look at, maybe you want to calculate the velocity in the y direction directly. And so you can use this expression, for example, for gas advection through a soil, right? Or through the ground, through the earth. And so K here is the permeability. So permeability's got units of square meters. Basically, how easy it is, how connected the pore spaces are in your medium. And mu is the viscosity of the gas that you're thinking about. And then PT is the total gas pressure in the pore space. So if you're dealing with, you know, the partial pressure of a gas in a gas saturated soil or something like that, you need to deal with the total pressure as a function of the vertical distance. And then you can get the gas density, which might be a function of the total pressure times gravity. So that you know would be an equation you could implement to calculate what the velocity field would look like for your buoyant gas. Then you can use the ideal gas law to get a handle on what that gas density might be. You can start adding a lot of complexity into this. So in other words, what I'm saying is you could use this expression to define what the velocity field is, right? The vertical velocity. And then you can impose whatever horizontal velocity you want on it, that kind of thing. So that's the advection diffusion equation. That's way too quick a tour of how we get the advection diffusion equation to work. In the context of tephra, and what I want to switch to and talk about next, in the context of tephra, basically we're implementing this equation. And there are different codes that implement the solution to this equation in different ways. So some models want to model the full atmosphere, right? So a good example of that is the ASH 3D code developed by the USGS, mostly by Larry Maston and colleagues, to forecast where tephra is going to go in an ongoing eruption. So what they really care about is, you know, say Mount St. Helens is erupting right now, or Colima volcano is erupting right now. Where is the tephra going to go, and how much is going to accumulate in a given spot? Well, in this case, where you're sort of now casting what's happening right now with the tephra dispersion, you might have a really good idea of what the components of the wind field are, right? You might know from meteorological models what the x velocity and the y velocity is. You can guess what the settling velocity of the particles are. You know, if you use Costanza's model, that's the you know, the rate at which particles are falling through the atmosphere. Some details about that are worth really understanding about tephra dispersion. So in the Stokes model, what happens is you can think of a particle being released in the atmosphere and reaching a settling velocity, right? And what the settling velocity is the constant fall of a particle, the constant velocity through an atmosphere of constant density. So in other words, it's easier to think about, say, dropping a relatively low density rock, maybe a dense scoria fragment, and you drop it in water. And the scoria fragment is going to accelerate until it reaches its Stokes settling velocity, and then it's going to settle at a constant rate through that water column as long as the pressure is constant around it, right? And so that's a pretty useful approximation for how things settle. So in Costanza's implementation, what she basically does is she finds the Stokes settling velocity for particles of different diameters, different densities, falling through the atmosphere with different densities, right? Because the density of the atmosphere is changing as a function of height. And the assumption in tephra 2 or in ASH 3D or FAL 3D or anyone, I think all tephra models, is that settling velocity accounts for the rate of particle fall. Meaning that what we do is we discretize the atmosphere into a series of layers. We say the density is constant in that layer. Not quite true, right? But we're approximating. The density is constant in that layer, and the particle rapidly reaches its settling velocity. That's not always true. So it's good to be aware of that. So one issue is that volcano particles are injected high into the atmosphere sometimes. So here's this expression phi. Remember, that's the source term. So I can say in my model, I'm putting tephra into the atmosphere at, say, 30 kilometers elevation above sea level, or 40 kilometers elevation above sea level. Well, what is the atmosphere like at 40 kilometers elevation? It's a pretty mean place. It's got a very low density, right? And so if it's a low density, it means the particle has to fall a long way, has to accelerate in order to reach for a long time, in order to reach its settling velocity. One time I did a calculation, every once in a while somebody says, oh, our column height was 50 kilometers. There was a point in volcanology where everybody wanted to find a volcano eruption that had the highest column height, some Freudian problem. But the column height of 50 kilometers, if you're releasing a particle from 50 kilometers above the Earth's surface, above sea level, and that particle's falling, it's actually not going to reach its settling velocity for a long, long time. So it will have already fallen through a big chunk of the atmosphere before it gets to a point where it actually hits the settling velocity, right? So in other words, what does that physically mean? It means, sure, the volcano can put the particles up at 50 kilometers, but they're not going to stay at 50 kilometers for very long. They're going to fall back down. And in fact, we saw that, right, in the Hunga Tonga eruption. Was it last year? 2 years ago? Anyway, the Hunga Tonga eruption, remember, the particles shot up to, very high. I can't remember what the final guess on the number was, but I think it was about 50 kilometers. And those particles shot up and then they fell down again, right? And they fell down very close to the volcanic vent and they spread out in an umbrella cloud. But that overshoot means that those particles basically did not settle slowly. They never reached a settling velocity that would allow them to spread in the atmosphere. So basically, if you get over something like 40 kilometers, the height of the column no longer matters, right? Because you're just putting the particle up and it's coming down really fast. Anyway, when you start looking at these expressions, those kinds of physically meaningful relationships come out of them, okay? And then there's this diffusion term. And in all tephra models, this diffusion term, K in this case, has two meanings. One is that particles diffuse in the atmosphere. Particles, you start with a bunch of particles and you release them in a sort of billiard ball type shape, and you drop them down an elevator shaft where there's no wind. They'll hit the bottom and they'll sort of spread out as a bullseye, right? The highest concentration will be at directly under where you dropped the ball from, but some particles will have, due to particle interaction and collisions and things like that, the particles are going to spread out, quote, diffuse over sort of a larger area at the bottom of the elevator shaft. So that's true diffusion in sort of a chemical sense or physical sense. And then often this term K is also used to capture other processes in an approximation of tephra dispersion. So what if the wind field's varying as a function of time? Well, you can try to capture that, and there are codes that do that, like puff or high split or codes like that, try to capture the change in the wind field as a function of time. But often in simplified codes like tephra2 or fall3D, we capture that as variation or increase in the value of K. That is, things are more noisy and there are processes that the model's not capturing. So sometimes you see that as well. And then the source term is pretty obvious. That's how much material you're putting into the atmosphere. Okay, so that's it for tephra dispersion. So let's go to tephra 2 and check this out.